We're starting with the paper ERNIE 5.0 Technical Report by the ERNIE team at Baidu, which dropped on February 4, 2026. This paper introduces ERNIE 5.0, which is a trillion-parameter, natally unified autoregressive foundation model. Now, the core concept here is a really stark departure from what we've been seeing with late fusion models. Instead of, gluing separate encoders and decoders together, ERNIE 5.0 trains text, image, video, and audio from scratch under one single objective. Next group of tokens prediction. The architecture uses an ultra-sparse mixture of experts, or MOE, with something they call modality-agnostic expert routing. This means tokens from any modality, text, image, whatever, get sent to a shared pool of experts. There are no artificial walls. A huge innovation here is the elastic training paradigm. So a single pre-training run produces a whole family of submodels. They can have different depths, widths, and sparsity levels, and you can deploy them for different resource constraints without ever retraining. And the result, it's achieving state-of-the-art, or at least very competitive results across language benchmarks like MMLU Pro, vision benchmarks like VBench, and audio, all while supporting this unified understanding and generation. Welcome back to AI Paper Podcasts. If you are a machine learning engineer, a researcher, or frankly, just someone trying to keep your head above water with the flood of new architectures hitting ERICs every morning, you are definitely in the right place. Today, we are dissecting a paper that really feels like it's drawing a hard line in the sand for how we build multimodal models.
It really does. I mean, for the last few years, we've been living in what I sort of call the Frankenstein era of AI.
Right.
You take a great LLM, you stitch a vision transformer onto it, maybe you bolt on a separate audio encoder, and you hope the gradients flow nicely across all those seams.
The classic late fusion approach. It works, but yeah, it's messy.
It's messy, it's inefficient, and honestly, it's brittle. Baidu's ERNIE 5.0 is basically saying stop gluing things together.
Right.
This is a trillion parameter model that is natively omni from step 0. It treats a pixel, a sound wave, and a word as essentially the same thing, just tokens in a stream.
Which is the holy grail, isn't it?
Yeah.
But usually when you try to do everything at once, you hit that ability seesaw.
Exactly.
Where you get, great image generation, but your text reasoning suddenly takes a nosedive.
Yeah.
Or your audio is crisp, but the model starts hallucinating code. The paper claims they've solved this.
They do claim to have solved it, yes. And if you look at the benchmarks, they're beating or matching models like Gemini 2.5 and DeepSeek v3.2, thinking they have the data to back it up.
But the how is what we really need to dig into, because it requires a complete rethink of the backbone, specifically this next group of tokens objective and something called elastic training, which frankly might change the entire economics of deployment.
Oh, that elastic training part absolutely blew my mind. The idea that one model can just shapeshift based on the hardware it's on. We definitely need to spend time there. But okay, let's start with the architecture, this unified autoregressive backbone.
Right. So the standard way to do multimodal is, it's usually siloed. Text uses next token prediction. Images might use diffusion. Audio has its own thing. ERNIE 5.0 just serializes everything. It maps text, images, video, audio, all of it into a shared token space.
So to the model, a picture of a cat isn't really image data. It's just a sequence of tokens that happens to decode into a cat. Exactly. But here's the nuance. Even though they're all tokens, the prediction objective shifts a bit depending on what the token represents. For text, it's pretty standard. Next token and multi-token prediction. But for vision, they use next frame and scale prediction. And for audio, it's next codec prediction.
But they're all optimized together.
Yes, simultaneously. And that optimization happens inside an ultra-sparse mixture of experts, or MOE. Now, usually when people build MOEs for multimodal, they define the experts. They say, okay, experts 1 through 10 are for images, 11 through 20 are for text.
It's a hard-coded specialization.
Right. ERNIE doesn't do that. They use what they call modality-agnostic routing. So the router doesn't check a tag that says this is an image. It just looks at the token's raw representation.
That feels, risky. Doesn't that mean you could end up with experts that are just a master of none?
Mm-hmm.
Or they get confused by the different modalities?
You'd think so, wouldn't you? But the analysis in the paper shows something fascinating. The experts do specialize, but they specialize by task, not just by modality.
Oh, that's interesting.
So you get experts that are really good at, say, fine-grained detail. That same expert might activate for a high-res texture in an image and for a really complex spectral detail in an audio clip.
That actually makes a lot of intuitive sense. Structure is a cross-modal concept. Reasoning is cross-modal. If I'm describing a complex scene in text or generating that scene in pixels, the underlying logic of what goes where is similar.
Precisely. And because it's ultra-sparse, we're talking about an activation rate below 3%, They can scale this thing up to 1 trillion parameters. You get massive capacity for knowledge, but for any given token, you're only paying the inference cost for a tiny slice of the model.
Okay, let's double-click on the vision side of this, because they treat images as single-frame videos. That sounds like a simplification to unify the pipeline, but how does that next frame and scale prediction actually work?
It's all about hierarchy. Instead of just generating pixels in a line, it predicts scales. So basically resolution first, and then it predicts frames or time. It kind of aligns with how humans see things. You see the gist of an image, the blurry shape, before you focus on the texture of the fur.
And to keep track of where everything is in that space, they use this UniRope.
Unified spatiotemporal rotary positional embedding. Yeah, it just assigns a 3D position to every token, frame index, height, and width. But the really cool engineering trick here, I think, is the bit flipping they do during training.
I highlighted that part. It sounded like they were intentionally breaking their own training data.
They are, and it addresses this fundamental weakness of autoregressive vision models. It's the telephone game effect. If you're generating an image token by token, and token number 50 is slightly off, then token 51 uses that bad data. By the time you get to token 1000, your image is garbage. It's error accumulation.
Fit flipping is like an inoculation against that.
Exactly. During training, they randomly flip bits in the history tokens. They corrupt the past. This forces the model to predict the correct current token, even if the history is a little messy. It teaches the model to self-correct. It's like teaching a student to solve a math problem correctly, even if they wrote a messy number on the previous line.
That's clever. It builds robustness right into the weights.
Yeah.
Okay, so on the flip side, visual understanding, they admit that compressing an image into tokens usually loses detail. You crush a 4K image down to a few hundred tokens, you lose the ability to read small text or see tiny objects.
And this is the classic CNN versus transformer debate, right? Transformers are great at global context. This is a picture of a beach. CNNs are amazing at local texture. This is a single grain of sand. ERNIE 5.0 uses a dual-path hybrid.
So it runs both.
It runs a CNN path for those perceptual details and a VIT path for semantic meaning. But the magic is in the fusion. They use an attention-based patch merger before quantization. So it fuses these two streams into a compact representation that still hold on to those tiny details you need for something like OCR, while also keeping the high-level concepts you need for reasoning.
And then, interestingly, for the final generation, if you want that super high-res glossy look, they admit the autoregressive backbone isn't quite enough on its own.
Right, and I really appreciate that honesty in the paper. Autoregressive models are fantastic for consistency, for getting the number of fingers on a hand right, but for that final polish, they use a cascaded diffusion refiner on top. It basically decouples the structure from the polish.
Okay, let's move to audio. This is usually the heaviest part of multimodal because the sample rates are so high. A few seconds of audio can become thousands of tokens.
Yeah.
If you just lay that out in a line, you blow up your context window almost immediately.
You do. So ERNIE 5.0 moves away from that horizontal line. They use a depth-wise architecture. It's based on something called residual vector quantization, or RVQ. Imagine an audio snippet. You can represent it with a semantic token. So essentially what was said. This is distilled from Whisper.
Okay, so token 1 is the text equivalent, like the word hello.
Roughly, yeah. But hello can be whispered or shouted or sung. Those are the acoustic details, the timbre, the prosody. Instead of putting those tokens next in the sequence, ERNIE pushes them down into the transformer layers. Layer N predicts the semantic code. Layer N+1 predicts the first residual detail. Layer N+2 predicts the next one.
Wait, so the depth of the neural network actually corresponds to the depth of the audio resolution?
Exactly. They're using the vertical capacity of the model, the layers themselves, to handle the complexity of the sound. This keeps the horizontal sequence length, the context window, totally manageable. It's what they call next codec prediction.
That is a really elegant use of the transformer architecture. It feels like they're exploiting the geometry of the model, not just treating it like a black box.
It is so efficient, but if we're talking about efficiency, we have to talk about elastic training. This, to me, is the most disruptive part of this paper for the actual industry.
I agree 100%. Because right now, the deployment headache is it's real. You train a 7B model for laptops, you train a 70B model for servers, maybe a massive one for the cloud. That's 3 separate training runs, 3 times the compute bill.
And 3 times the maintenance. ERNIE 5.0 proposes this once-for-all paradigm. They train a single super network, but during pre-training, they apply randomness to the structure itself.
A bit like dropout.
It's like dropout on steroids.
Yeah.
They have 3 dimensions of this elasticity. First is elastic depth. They randomly drop layers about 25% of the time during a training step. This means the lower layers are forced to become self-sufficient. They can't just rely on the top layers to fix their mistakes.
Which means later, for deployment, you can just literally slice off the top 20 layers and the model still works.
Exactly. You get a shallower, faster model for free. Second is elastic width. They randomly wrote tokens to fewer experts, say a subset of 32 instead of the full 64. This lets you deploy in memory-constrained environments where you physically can't load all the experts into VRAM.
And the third one.
Elastic sparsity. And this one is cool because it targets latency. They randomly reduce the top K experts per token. So normally, maybe the router queries 8 experts for each token. But sometimes during training, they force it to only query 2.
So the model learns to get the job done with less help.
Yes. And this doesn't change the model's file size, but it drastically changes the inference speed. So if you're on a mobile device and your battery is low, you switch to top 2 mode. If you're plugged in, you go back to top 8.
Now what's the performance hit?
It's minimal. They showed an elastic model running with only 53.7% of its parameters activated, retaining almost full performance. An average score of about 75 on benchmarks versus 75.5 for the full model.
That is a negligible loss for having the compute.
Yeah.
It completely changes how we think about the model.
Yeah.
It's not a static binary anymore. It's this fluid thing that expands and contracts.
It turns the model into a dynamic asset. You don't download the 7B model. You download the model, and your software decides how much of it to inflate based on your hardware state at that exact millisecond. It essentially solves the whole edge versus cloud dilemma by making the model adaptable to both.
I want to shift gears a little to the post-training section, because training a trillion-parameter multimodal model is hard enough, but doing reinforcement learning on it just sounds like a complete nightmare. The paper mentions entropy collapse. Why is that such a specific risk here?
It's the curse of high-dimensional spaces. When you do RL on these massive models, the model tends to find the path of least resistance. It realizes that short, safe, generic answers will minimize any penalty. So the entropy, the randomness, the creativity, it just collapses. The model stops exploring.
It becomes a boring, safe bot.
Right. And since they're training on text, vision, and audio at the same time, the numerical instability is huge. The gradients from an audio task might look totally different from a text task. So they implemented a few fixes. One is algorithmic J-mixed ice pop.
Which I assume is not a frozen treat.
Sadly, no. It stands for a modification of GRPO group relative policy optimization. Basically, it uses multi-granularity importance sampling clipping. And without getting totally bogged down in the math, it fixes the numerical mismatch between the inference engine, which generates the output, and the training engine, which calculates the gradients. It just keeps the training stable so the model doesn't panic and collapse into that safety mode.
They also mentioned a well-learned positive sample mask.
Yeah. That's all about efficiency. If the model already knows the answer to what is 2 plus 2, with high confidence and stable entropy, stop updating the weights based on that question. You stop wasting gradients on easy wins. You just mask those out and focus all the updates on the hard stuff.
But focusing on the hard stuff creates another problem, doesn't it? The long tail problem. They talk about the unbiased replay buffer, or URB.
This is a classic engineering bottleneck in RL. You generate a batch of answers to learn from. Some are short, like yes. Some of these long, complex math proofs. The GPU batch has to wait for the longest answer to finish generating.
So the whole cluster is just sitting there stalled, waiting for one slow query.
Exactly. And the old fix this thing called April was to just cut off the long ones or recycle incomplete ones. But think about what that does to the model's behavior.
It biases it against long, complex thinking. It learns that long answers get cut off, so it just stops producing them.
Bingo. The URB is this complex buffer system that enforces data ordering. It decouples the inference pool from the training pool. It allows the long, hard queries to finish in their own time, and then it inserts them into the training batch later, making sure the model actually trains on the hard stuff without stalling the whole pipeline.
And what about when the model just fails completely, like it tries a hard math problem and gets zero reward because it's just wrong? It can't learn from zero signal.
That's where they use adaptive hint-based RL, or AHRL. They inject think skeletons, these partial hints, into the prompt.
Like a teacher saying, okay, start by factoring the equation.
Precisely. It scaffolds the reasoning, and as the model gets better, they use annealing to slowly remove the hints until the model is solving it all on its own, independently. It's a very human way of teaching.
It really highlights that at this scale, it's not just about the architecture. It's about the engineering pipeline you build to actually train the thing without it collapsing or stalling.
And speaking of the pipeline, let's hit the infrastructure before we wrap up. They did something interesting with the tokenizers.
They disaggregated them. This is just smart systems engineering. Video processing is computationally heavy. Text is super light. If you put them on the same GPU, the text part just sits there, idle, while the video part crunches numbers.
So they physically separated them.
Yep. They put the visual tokenizers on totally different physical nodes. The backbone just requests tokens and gets them. It balances the load across the entire cluster and prevents that starvation scenario where the fast components are waiting on the slow ones.
Yeah, flash mask. That's a custom operator. Because text is causal, it looks backward, and images or bidirectional patches look at each other, the attention mask gets really messy. Flash mask is a custom kernel that handles these mixed patterns about 200% faster than flex attention. It's a low-level optimization, but when you're training at this scale, those milliseconds add up to millions of dollars.
So all this engineering, all this unified architecture, does it actually pay off in the benchmark?
It really does. In text, ERNIE 5.0 beats or matches DeepSeek v3.2 thinking and Gemini 2.5 on knowledge tasks like simple QA and coding tasks like human eval, plus
That vision.
very strong on VBench for video generation. And for audio, it has competitive word error rates on LibreSpeech. The key takeaway isn't that it's number one in every single tiny metric, but that it's top tier across all of them simultaneously. It validates the unified thesis. It proves you don't need a specialist model for each mode.
Which brings us right back to the big picture. What does ERNIE 5.0 signal for the future?
I think it signals the end of the patchwork era. We're proving that native omni models are viable at the trillion parameter scale. And the complexity of gluing models together is being replaced by the complexity of building these unified training pipelines.
And for me, the elastic training is the real lingering thought. We're moving toward a future where AI models aren't these massive, unwieldy files we struggle to run. They're fluid. Imagine an AI on your phone that's a 1 billion parameter model when you're hiking and low on battery, but it expands into a 10 billion parameter model the moment you plug it in, instantly unlocking deeper reasoning capabilities without you downloading a single thing.
It completely changes the relationship between software and hardware. It makes AI infrastructure dynamic instead of fixed.
It's a fascinating report.
Yeah.
If you want to see the math on JMixed IcePop or the Unirope embeddings, we have linked the full paper in the show notes.
Definitely worth a read for the engineering details alone.
That's it for this deep dive. Thanks for listening, and we'll catch you on the next one.